Okay, so let us start. So last week we were doing binary heap implemented as a complete binary tree or close to a complete binary tree stored in an array. And for that we have that dictionary, how to convert array locations into the tree locations. So how to convert this 1D into 2D. We had those formulas. So essentially the parent of jth node will be present in j minus 1 by 2 and the children will be present in 2j plus 1, 2j plus 2. Okay, just a multiple by 2 or halving. And so the advantage of complete binary tree is that for n nodes you will get depth only log n. So basically all the levels are full except the last one. So the leaves may not be, or may not, so all of them may not be present, but whatever is present on the left side. Okay, that is the meaning of complete binary tree. And so min of the heap is just 0th element in the array. Extract min is you basically swap h0 with hn minus 1, first with 0th with the last, or first with the last in the array, and then delete the last, and after that you do this process which will preserve the heap axiom. So this takes time only height of the heap, okay, which is bounded by log n. Insertion was add in the end, and then after that again try to maintain the heap axiom by going up. So insertion again takes log n time, and similar thing with decrease key. So any questions till now? So all these operations are very similar and they take height of h much time. So log n time. So the last one, which is the most complicated one, is the merge operation. So you are given two heaps, h1 and h2, again as implemented as array, and you want to combine them into and get a single heap. So n here is the size of h1 plus the size of h2. Okay, that is the input size. For this, can you use insert? Can you use the insertion subroutine to merge h2 into h1? So basically extract min from h2 and then insert it in h1, right? So you can do this repeatedly. What will be the time? So in this case, insert has to be called and each time it takes each call it takes log of h1 time. Okay, so you have to call it h2 times, and every time, since you have to insert this element in heap h1 and you don't know what the element is, don't have any properties on the element, so it may take maximum height of h1 much time, that much time. So it's h2 multiplied by log h1, which is, in terms of n, it will be n log n. Okay, so if you do this just using the previous subroutines from the last week, this will take you n log n time, the same time as sorting. So the question is, can you make this linear time? Okay. So how do you do it faster? So heapification is a process which will do it in linear time. Okay, so what we will discuss is called heapification. So you are given two arrays which you can actually just concatenate. So you are given a single array, and that single array is not yet a heap. So you want to turn it into a heap. So an array of size n, when you turn it into a heap, is called heapification, and we'll give a process which takes linear time. Okay, this is a very general process, works with an array. So here the idea will be turn any array into a heap and carefully analyze the time. Okay, so what does this, what does careful analysis mean? So this we will see. It will be a nice estimation which will come out to be linear time. It will use the properties of the complete binary tree. Okay, so let us do this now in detail. Write the pseudocode for heapification. So the input is an array indexed elements index 0 to n minus 1. It has, let's say, positive integers and arbitrary order. Okay, so there is no assumption on how the integers are, except maybe you can assume them to be distinct. So these are distinct integers, n integers in arbitrary order. In the output, you want to make it a heap. Of the same size, of course, right? And in the same array, so things will be, integers will be moved around, and so in a way so that in the end it becomes a heap implemented as an array. Right, so this is the heapification problem. So the idea here is start bottom up. In the heap locations, and ensure the heap property. At every step. Okay, so same thing that you have been seeing since extract min. So you are currently at some location j of the array, which maps to some location in the heap as a tree, and you have to check basically the children of j and the parent of J and ensure that the heap property or the heap axiom is correct, is being satisfied. If it is not being satisfied, then for example, if one of the child is smaller in value, then you swap the value. So when you swap the value in the heap as a tree, you swap the value in the heap as an array, right? So you'll just exchange the two values. So this you do and accordingly either move down or up, and in general you will start from the level just above leaves, second last level, and from there you will go up. Okay, so remember the array initially was arbitrary, so everywhere the heap property is being violated, so you have to start from somewhere. So it is best to start from the leaf, and just above you will see the violation of heap axiom. So you exchange there, and then you move up. When you reach the root, then it's a heap. Well, even then it may not be a heap, because when you exchange the root value with children, maybe more modifications will be needed, so then you will come down. Okay, so you go up, you come down. But every time you get closer to a heap. So let's see an example in case we have forgotten this exchange trick that we have. So So this is the heap array. So the array will, if you recall the syntax, the array will be the first element, the 0th element is 14, right? So the array looks like this. So 14 and then the children, and after this, what comes after 11? Yes, you just read from left to right, top to bottom. So 37, 11, then 85. So that is the array. Goes from 0 to whatever this is, 0 to 8. So this is an arbitrary array. So the first step that you will take for heapification, to do heapification, is you look at this second last level, which is 85, 17, 25 and 13. And there do you see a violation of heap axiom? At 85, right? So at 85 there is a violation. So what should you do here? Yeah, so 85, you look at the children, minimum is 47. So you should just exchange with that. Yeah, just look at the second last level. The level of height 1, look at that. And then from there you go above. So height 1 here is this level that starts with 85. So there you see the first violation already. So notice that it is violated by both the children, but there is no point exchanging with 75 because this still will continue the violation. So it is best to actually exchange with the minimum child. So exchange with 47. So Yeah. Yes, but I think if you are coming from the left to the root, then you still not have seen the right part. So you have to ideally see all the elements before you are sure that it is done. So you may have to come down. But that we'll see. So this is only the first step. First step is bottommost internal node. Okay, so look at the bottommost internal node where there is a violation, and then you exchange with, then you correct that locally. So local correction will give you, let's go to the next slide. Okay, so that is the heap. Only change is 85 is exchanged with swapped with 47, right? So now what is the next violation? So 47 is fine. The next violation will be, yeah, you are moving up, so 37. And that should be swapped with, so again next bottommost internal node where there is a violation, right? So that only parent-child relationship you can see is in 37 or 11. You start with 37. You see the violation, so you now swap with 17. Yes. The pointer in the array is moving haphazardly because there is actually no tree pointers, right? This behind the only access you have in the data structure is an array. Yeah, yeah. So you move by halving or doubling. Yes. So when you double, you go to the child. When you halve, you go to the parent. So that is the. So this is why this is a more complicated topic than what you have seen before, because here it's actually an array where you have to visualize as a tree. In the data structure, it is not tree pointers. There are no pointers. So there is only arithmetic. Correct. Yeah, so you might have to go down. But let us continue with this example. So, yeah, so hopefully this is correct. It's the same heap. Only 37, 17 is exchanged. Next what? So next you see the wherever you are, which is right now you are at 17. So its parent has a problem, right? 14 is not minimum. So now you have to go in a different direction. From this left subtree, now you have reached the root, so now you will possibly move to the right subtree. In this case, it's necessary. So you exchange, because you have to exchange with 11. So you get 11. So 17 part is now done, and 11 has 25 and 13. Where is the problem now? Yes, so 11 and the left part is covered. That's a sub heap. But when you bring 14 down, everything below that is untested. So you have to test it. So now the suggestion that was given will apply. You have to check axiom at 14 and you see that it's violated. Right, so you have to do something with this. So that will give you 14 and so this becomes 13 and 25, 14. Okay, so this is the final heap. Is this clear? Heap H and already implemented as an array, because you can see that the skeleton of this complete binary tree was not disturbed. Okay, so there is still this complete binary tree, and moreover it satisfies all everywhere heap axiom, heap property is there. So maybe we can write that. So what it has become is now this. So 11 okay, so that's the this is the heap array implemented as an array. Okay, so you started with the input was this green array, which was which is surely arbitrary looking, but even as a heap, even as a tree, it is not a heap. And you end up with that green array, which when seen as a tree, you can check is a heap. Okay, so this is the input to output. This process is called heapification. Is this fine? So now you have to see the pseudocode of this. Right, this is a complicated pseudocode. So when at the ith node, we call that step, the thing that we are doing in this example, we call it heapify. So what this heapify step, when you are at node I in a given array H, as a tree, underlying tree does is it checks value of Hi with its children, and if needed, it goes down. Okay, so it exchanges this I with its min child, and if there is a need to go down, then you will do that, which we did at the root. So what this will ensure essentially is that below I, the subtree below I, that becomes a heap. Okay, so recursive, so this is the invariant it ensures, that at I as a root, you have a heap structure. Okay, so this is the invariant that you need to remember about this subroutine. So let us now write its details. So n, the size of the heap is n, which is at least 2. Okay, we'll assume that. And now how do you make things below I a heap? So maintain a flag, initialize to true. And while you have not reached the lowest level, which is n minus 2 by 2. So these will be the iterations under the while condition. So at this node, we initialize min to I. But if one of the child is smaller, then you need to update the min. So which child is 2i plus 1 of I? Left, right? So you have checked the left child. If it is smaller in value, then you call that the min. But you are yet to check the right child. So now you also check that. So if the right child is even smaller and it exists, so this is simply a boundary condition check because you don't want to overflow the array. So if it exists and it is smaller, then you update min to that. So you may picture this as follows. So I has 2i plus 1 and 2i plus 2 as children. And the height of I is h. Okay, so you are at height h from the bottom of the tree, and these are the children. You have checked all three, pick the minimum, stored in min till now. So if minimum is not the ith node, then you have to swap. So swap hi and h min. And when you swap, then you have to move down. So you initialize I to that location. So this is where you are going down. else flag is false. Okay, and that ends the while. And what else was there? There was the function that now ends. Initialize, no, heapify is just a function. There will be a main program which will call this. So that main program you can now guess and write. So the main program will essentially, like we did in the example, the main program will locate this lowest level internal node, like 85, heapify, call heapify on that, and then move up. So call heapify on that, keep moving up. Yeah, because this is only a short function. There will be a function which will call this. Yeah, this is only for above this there is another loop in the main program. We don't want to write everything. So it suffices that we just discuss, so there are many orange steps in the example. One orange step is this. Okay, and there is a main program which will call this function heapify, I starting from the bottommost internal node, and then keep calling it again and again till your H becomes a full heap. So one step in our dry run of the example, this is what is happening. Is this clear? And then this is called again and again. So main program calls heapify on the bottommost node and goes up. Till you reach the root. Once you reach the root, then that heapify call will finish everything. Okay, so this is the full heapify pseudocode, and heapification is just a main program which will work with this, going from bottommost to topmost. And so why is this fast? Right? This time complexity of this pseudocode is not so easy to analyze, because this is the main program is going from bottom to top, but then within heapify also it is moving down. So you have to actually keep track of how many times you move up and how many times you move down. Right? So this is not just a single moving up or a single moving down. It's actually something is being repeated. So we cannot just say height of H. so we have to analyze this. Since this moves up and down H repeatedly, we don't have an easy analysis. So the complexity analysis is tricky. So let us let's do this carefully. So we have that picture of Heapify at I. What we claim is that I mean, ultimately we will get linear time, but let us see how. So you look at what is happening at height h. So height h can go maximum up to log n, because at all points of time we are maintaining the complete binary tree skeleton, right? So at no point is the height more than log n. So the h variable varies only from 1 to log n. Now for a given height, what is happening? So internal node V at height h does what? So there you are calling Heapify. So let me change this to V. So you are calling Heapify on V. Okay, so we have basically divided all the nodes in terms of the height where they are. So in other words, we fix the height h, and then we go over all the nodes V at that level. Because once you have called Heapify on a node, you will not be calling it again. Right? Heapify on a node is called only once. So we have partitioned Heapify according to the heights, and then within a height or a level, we take the sum over all the nodes V. So this is what we want to estimate. Time is some constant multiple of this. Is this clear? Okay, so how do you estimate this? So this is less than equal to well, so it is clear that if the height is fixed and you are only changing V's, the time is the same everywhere. Right? Because the basic structure of the tree at a height h is the same everywhere. So this time is the same everywhere. So we just have to multiply that time with the number of nodes at that height, which I am calling nh. So nh is the number of nodes at height h. Okay, so time of EP5 for a node is, is this clear that it's order h? EP5 for a single node is just because you just have to look at the pseudocode. Well, in the pseudocode, you can see that we are only going down, not up. Right, so here itself, here there is no confusion. So this will only take as much as is the height of I, node I. So that the time for EP5V is just given by the height, which is order h. And then it is the same for all the nodes V at that level. So you multiply it by the number of nodes, that is nh. Fine till here? So after this, it is easy, because now all you have to do is put the expression for nh. So what is nh? So nh is, let me just put it directly, it is this. Why is nh less than or equal to n upon 2 raised to h plus 1? So how many nodes are there at height 0? H equal to 0. It's again, it's coming from the skeletal complete binary tree. Right, the complete binary tree, the numbers are concentrated in the leaf. So half of the tree lives in the leaf, in the leaves. Right, so if the tree is of size n, then n by 2 is the number of leaves. It cannot be more than that, it's less than or equal to that. So for h is equal to 0, it is n by 2, and then as you go up, you just keep halving. Okay, so at height h, it is n divided by 2 raised to h plus 1. Clear? So this comes from the fact that our pseudocodes will always maintain the complete binary tree skeleton. Any questions? Then what? What is this sum now? So this is now just a simple calculation. So age goes from 1 to log n, and you have, let's take out the big thing which is order n and multiply it by this. Okay, so we take out order n because that doesn't depend on h. And what depends on h is just h upon 2 raised to h plus 1. So that we have separated. What is that sum? So that sum is almost like the sum of 1 plus half plus 1/4 dot dot, right? It's constant. Even if you put an h there, the halving is getting so big that overall the sum is an absolute constant. Okay, so this comes out to be just a constant. So what you get is order n. Clear? So this you can do as an exercise. So first prove that the number of nodes at height h is n by 2 raised to h plus 1, and then show that the sum of h over 2 raised to h plus 1 as h goes from 1 to infinity, it is always a absolute constant. So the only contributing term is n. Okay, this is a linear time algorithm. So let's just collect that as a theorem. Okay, so heapification of a size n array takes only linear time. So it is significantly faster than sorting. Okay, this somehow should be connected to sorting. So it is, there is a connection. We'll see that very soon. But this can be done faster than sorting, just in linear time. Can this be faster than linear time? It cannot be, right? Because in the heap, everywhere the axiom has to be checked. If you miss a single element in the heap, if you don't check the heap axiom, then one may adversarially fix that element. Right? So the axiom has to be checked at every element, which means that you have to check at least n by 2 places. Nothing can be missed. In fact, you have to check all n, nothing can be missed. So linear is the fastest possible, and we can do it. Yeah, so that's a very nice algorithm. And based on that, on this, you immediately get the heap sort algorithm for sorting. So how do you use this to sort an array? It's very simple. You are given an arbitrary array of integers. You heapify, so after the heapification, extract min, then again heapify. Right? So, and then again extract min. So that will give you the sorted array, at least sorted output. So build heap, so in the input you are given, I think we don't have time for too much detail. So let me just say, given this array A, build heap H, and print extract min H, and then repeat. Okay, so that's all. Given this arbitrary array of integers, build the heap, extract min and print the value, and then repeat this. So whatever remains in the heap, n minus 1 elements remain, again build the heap, extract min, print it, and go to the next. Okay, so this will only take, building the heap through heapification takes linear time, and extract min takes height of the heap, right, which is log n. So the product of this is n log n. So that is the sorting algorithm. So heap sort takes order n log n. So you have learned 3 algorithms already. So merge sort, quick sort, and heap sort, right? They are all similar time, n log n, and you cannot do better than this. Okay, so next time we'll finish this and move to more problems, tree-based data structures.